signal in each sensor for each frequency. And then we have Y2F and so on until we have YMF. So we have M sensors, and then we process the signals for each frequency independently. So our model is that YMF equals to some vector which is multiplied with the desired signal. Okay, so it looks like that. XMF, which is the desired signal in that sensor, plus the noise. And we saw that we can write it as the relative transfer function. We can write it as GMF divided by G1F X1F plus VMF. So this is the relative transfer function, which we saw we can estimate it from the observed signals under certain conditions. And then we saw that we can define a vector. So this vector contains the measurements from all the sensors. So we have Y1F up to YMF. Transpose. So this is vector of measurements for the frequency F. And from this vector of measurement, we want to estimate the desired signal in the reference channel, in the reference sensor. Okay? So we can write this as equal to a vector of M measurements. Let's write it like this. But because the desired signal is correlated. Okay. But because the desired signal in different sensors is correlated, it's okay? Backward? Like this? Yesterday it was okay. Maybe we need light. Maybe the light will help. Okay, well, you're the professional. Okay, just whatever you say. Okay? It's good? Okay. So when we have this model that the measurements, vector of measurement, m measurements, the number of sensors for each frequency f, it equals to the desired signal in the vector of sensors, plus noise in the vector of sensors. But the advantage is that we can write it in such a way that it is related to the desired signal in the reference sensor by writing it like this. D, which is a vector, D f, multiplied with a scalar, x1f, plus vf. Okay, so if we write it in such a way, so when we go from here to here, we assume that we know this vector. Either we know it, we know how to estimate it, and then it gives us a lot of information. Actually, this is called the steering vector or propagation vector. And we can obtain it actually from the measurements of the coherence function between x and x. Okay? So we saw that D, the steering vector, equals to the coherence. So I want to use the same notation that we used before, okay, just to check, because you need to be consistent. See, so it was here. Let me check. Okay, so it was here. This is the model. And we saw that the vector, this vector, which we assume that we know, it contains a lot of information. We know the direction of the signal, but not only the direction. We know, including all the reflections from the desired source to each of the sensors, which is a lot of information. So we know this relative transfer function. And this relative transfer function is actually, you see, equals to the correlation or the gamma, the joint complex conjugate between x1 and the vector x. Okay, I have it here. This is an element here. See? And this, suppose that we measure in the sensor array, we have measurements of the correlations between x1 and x. It's called the coherence function, or partially normalized coherence function, which we can measure that or can estimate it once either from noisy measurements or even better from clean measurements using the sensor array. So we have that this is the way it is defined. So actually, this propagation vector or steering vector or coherence function, partially normalized coherence function, all similar names. It depends on the application where you use it. But what you need to understand, that this contains a lot of information. First, where the source, the desired source, which direction it comes from. Also, reflections in the environment. If it includes reflections, it will include in the transfer function or relative transfer function. And also, it depends on the configuration of the array, where you put the sensors in the environment. So all of that information, we use it in this vector. And then we try to estimate this scalar, which is the component of the desired signal in the reference sensor. So we can try to obtain an estimate of x1f from this vector of noisy measurements. That's why it looks like that. linear filter. Okay? So we saw that we can write it like this. So we need to find an optimal filter of length m. For each frequency is different, this filter, of course, because we work independently for each frequency. So we optimize it for each frequency and multiply it with this vector of m measurements for the frequency f. Okay? So in order to find for each frequency an optimal filter, we need to define the performance measures. So the performance measures, we defined it yesterday. Okay, so we defined the performance measures, signal to noise ratio, input, narrowband input, broadband input, narrowband output, output SNR, narrowband, output SNR, broadband, which we integrated, takes summation over all frequencies. We defined the noise reduction factor. As we know, noise reduction factor, it's the amount of noise reduced compared to the reference sensor. Okay, so if we take this output, it contains two components because everything here is linear. So you see, working with linear filters enables us to define things which are easier to derive. So we can write it as X filter desired plus residual noise. So we can check the variance of the residual noise. What is the variance of the residual noise compared to the variance of the noise in the reference sensor? So this is noise reduction factor. And we can also, so we can define narrowband and broadband for each performance measure. And then we can also define the desired signal reduction factor. Okay? So narrowband and broadband, desired signal reduction factor, it means what is the variance of X filter desired compared to the variance of the desired signal in the reference sensor. Like Christmas, snowing. Okay, so desired signal reduction factor, and then we have also the distortion index, desired signal distortion index, narrowband and narrowband and broadband, which means how the desired, what is the mean squared error between X filter desired and X1, what is the mean squared error between them? And it's normalized by the variance of X1. So this is the distortion. As we know, it's similar to what we defined for single channel frequency. And then we can define also the mean squared error, narrowband and broadband, which is the mean squared error between the estimate, the total estimate, and X1. So of course, it includes two parts. One is the mean squared error because of the distortion, and one, the mean squared error because of the residual noise, like this. You see, here. So the mean squared error can be defined as it consists of two components. One is related to the distortion, and one is related to the residual noise. And okay, so if we try to minimize the mean squared error, we'll get the winner. If we try, we can ask which filter here will maximize the SNR, which will give us maximum SNR. So if we write the output SNR, we have this expression. So we saw that any filter that is proportional to phi v minus 1 d, which is gamma complex conjugate of gamma, partially normalized coherence function here. And these are zeta any numbers which are different than 0. We get filter that maximizes the output signal to noise ratio. And we will see that this is for the narrowband, okay? We will see that the other filters that we will discuss, some of them you know, because we discussed it for the single channel, but we will also discuss about LCMV and generalized side lobe canceller structure, which are very important for multi-channel signal enhancement and also for beamforming in the frequency domain. So this will be like new material, so we will discuss this. So except the LCMV and the generalized side lobe canceller, all the filters look like that with certain. So we have this variable. So the only difference between them is with these values. So you see we choose here a scalar value for each frequency. But if we change it, you see it doesn't really affect the narrowband output SNR. You see here. If I take a filter H, a vector for each frequency, and if I put here, again, a certain scalar value, and I multiply for each frequency here, the filter, I multiply it with a scalar value, complex value, okay? So you see that it cancels out in the numerator by the denominator, okay? That's why when you compare, so suppose that I have other filters. We will talk about the Wiener, the MVDR, the trade-off. We will see that all of them are proportional to phi, just like I said here, okay, to phi v minus 1, to this matrix, which is m by m, multiply with the vector of the partially normalized coherence function. So all of them, what does it mean? It means that if the other filters like Wiener, MVDR, and trade-off, if they are, the only difference is this value, it means that all of them maximize the narrowband signal to noise ratio, the output signal to noise ratio, as we will see. The difference, but they don't maximize the broadband output SNR, which is important. Okay? If you remember, if you rehearse the material of the single channel, so you remember that with single channel signal enhancement, we worked with gain for each frequency. And then with gain for each frequency, the output SNR was the same as the input SNR for all the filters. But the broadband output SNR was different. So we were able to maximize the broadband output SNR. So here, because we work with multi-channel, multi-sensor, we can find a vector, a filter, a vector of length m for each frequency, such that it will maximize the output SNR. But any filter that is proportional to this vector, if we multiply it with a scalar complex value, we obtain that the narrowband output SNR will be the same. But it's not equal, it's not maximizes the output, broadband output SNR. Okay, so the differences between the filters are actually, even for this, by this value, and these values, actually the effect of the trade-off between signal distortion and noise reduction, maximization of the SNR, and so on, of the broadband measures is determined by these values. These values are very important. And actually, this is a very nice thing, is that if you take the expression for the output SNR using this, okay, using this vector, you see this is a vector. And you can take any values here, which is proportional to this. So I can compute the output SNR in the expression that we saw before. And this value zeta, we can cancel that in the expression of the output SNR, just like we saw. So if I use this vector and I put it in the expression of the output SNR, when we have M sensors compared to when we have M-1 sensors, and compared to, so we can show mathematically, and this is a nice exercise if you want to show it, to prove it. So the output SNR, you can use that vector, and it's possible to show that the output SNR is a increasing function of the number of sensors. So the more sensors that you use, the output SNR will increase using this derivation. So it's possible to show it, and it's a nice result to show it also mathematically. So it shows that no matter which signals that you choose, always when you add some sensors or you add a sensor, the output SNR will essentially be larger or equal to M-1 sensor. What do you think? Okay, so first, intuitively is trivial, right? Because if you add an additional sensor, you have more information. So it will improve the output SNR that is achieved by the maximum SNR filter, of course. So my question is, when do we have inequality? When it doesn't increase, but is equal. So if I add a sensor, additional sensor, and the output SNR that is achieved using the maximum SNR filter is not larger, but is equal, remains the same. What does it mean? What? Exactly. So the additional sensor, it doesn't include any information, new information. So it doesn't include the information regarding the correlation. So maybe this additional sensor will not have, think about, suppose that we add an additional sensor and it doesn't correlate the desired signal that is received in this additional sensor does not correlate with X1, with the desired signal in Y1, in the reference sensor. So it will not add significant information that we can use in order to better estimate X1. So it will not add information, and therefore there will be some equality. So remember, you asked a question, if we have sensor that maybe it doesn't add information, maybe the sensor is fault, it doesn't collect real data. But even if we put it somewhere and it doesn't correlate with the signal received in the reference sensor, it means that it's not useful. So it will not add useful information, and therefore we will not improve the performance. Example, did we see this example yesterday or not? No? Okay. So in this example, suppose that we have a signal like this. So we have capital T samples of sinusoidal signal with a constant amplitude and frequency. F0, and the phase is randomly distributed or uniformly distributed on the interval between 0 and 2 pi. So if we have this signal, and suppose that the direction of the desired source comes from theta 0, okay? So the desired source, suppose that this is the array. This is sensor number 1, 2, 3, and so on. And suppose that the desired source comes from theta 0. And there is an interference that comes from the end fire. Okay? So it comes from this direction. Let's call it UF. It comes from the end fire, from theta equals to 0. And in addition, we have thermal noise. Okay. So what do you think if we want to compare the maximum SNR filter? We want to increase the output SNR, the ratio between the variance of X filter desired compared to the variance here, using a fixed number of sensors, fixed number, M, a fixed number, I don't change it. If theta 0 equals to 0, or we increase theta 0, do you think what will happen? Can we improve the performance? If theta 0 equals to 0, which means that the desired source and the interference come from the same direction, do we gain some improvement of the signal to noise ratio if we add sensors? What do you think? Okay, so you said no, but I remind you, I said that we have also thermal noise. Okay, so compared to this component, the directional noise that comes from this direction, we don't improve. If we add more sensors, we cannot reduce this more efficiently because they come from the same direction, so one sensor or multiple sensors, the same performance regarding these noise components. But regarding the thermal noise, of course, we can reduce it to some degree. Not too much, based on the number of sensors, so it goes like the power will go like square root of this, of the number of sensors. So the power will be reduced inversely proportional to the number of sensors, which means that we reduce the noise by the square root of the number of sensors. So we can reduce, but it's not much. We need many, many sensors in order to average the thermal noise if they are independent. So let's see what happens. So in this example, by the way, we can compute the correlation matrices and so on. I encourage you to follow these expressions, okay? I'm not going, because it's an extension of the single channel, but I encourage you to follow this expression, how to compute the correlation matrices, phi v and phi x, and so on. Okay, and we can have an expression for the gain in SNR, specific expression based on the direction of the interference. Okay, so the directional interference. So we have this expression. And I encourage you to follow the step one by one to see that you understand how to do that. So in this example, I assume that the variance or the power of the thermal noise is 1% of the directional noise. So the directional noise is much more significant compared to the thermal noise. Okay? So if we see here the gain in SNR, so this is the improvement of the gain in SNR as a function of M, as a function of the number of sensors for different frequencies. So here the frequency is 0.01, here it's 0.05, here it's 0.1, here it's 0.2 for different frequencies. But let's look at here. What is the gain in SNR? So we see that when, so the blue line is for theta 0 equals to 30 degrees. The green is for 50 degrees. And then the red is 70 degrees. And the last one, the cyan, the light blue, is 90 degrees. So you see that if the direction theta 0 is fixed, we don't change it, it's fixed. When we increase the number of sensors, when we increase M, the gain in SNR increases. See? When theta 0 is fixed. Okay, now it's interesting to see that if M is fixed, if we use a certain number of sensors, M, when we increase theta 0, between, it becomes larger and larger, up to 90 degrees. The spatial separation between U and X0 and X, which means the spatial separation between the direction of the desired source and the interference, becomes larger. So we are able to suppress more noise. So we increase the gain in SNR. The output SNR will be higher. Okay? So I didn't show here for theta equals to 0, theta 0 equals to 0, which means that they come from the same direction. So you can try it yourself. You have the MATLAB code. You can follow that. You can ask different questions. You can change the signal. So it doesn't depend on the signal, okay? It makes sense because what we try to do here with the filter H for each frequency, what does it do? Any filter, not only the maximum SNR. Here, with the maximum SNR, I show the gain in SNR. But I can show with a different filter compared to the performance measure that I obtained, the optimal filter that obtained, that was derived based on this performance criterion. So if I try to find the optimal filter, so you see the optimal filter, it takes into account the correlation within this vector. What does it mean, correlation between these vectors? Correlation between any two desired components in this vector, and correlation between any noise components in these two vectors, which depend on the configuration of the array and so on. Okay? That's why when we have when we use this correlation, okay, so when we separate them, actually we're able to create spatial filter such that it is directed to the source and suppresses undesired components from a different direction. So as you know, when I talked about overview of multi-channel signal processing, when we get like a steering direction, main beam, or beam pattern that is directed to the direction of the source, there is a certain beam width. So if we use a certain number of sensors, and then we have a certain beam width, and we have also side lobes, which means how much can we reduce these noise components. So what we're trying to do is actually to obtain, to keep the desired signal only from a certain direction, and suppress as much as possible interference from undesired direction. And we try to do that using this filter. So it's spatial filter. So if this direction, the desired direction and the undesired direction, they are close to each other, it's more difficult, which means that it's more difficult, so the performance will be less. You see, the blue line is below the other one, because the separation, spatial separation, only 30 degrees. So in order to improve the performance, they need to be from different directions. This is one observation, which is obvious. Alternatively, if you want to improve the performance to separation between different directions, you need to increase the number of sensors. Okay? Okay, this is intuitively, it makes sense because we talked about it, about multi-channel. But I also want to show you the relations between different frequencies. What happens when the frequency is higher for higher frequency components? So you remember that even when the array is fixed, suppose that we choose 10 sensors. And the separation, suppose that the separation between the source, desired source, and the interference is 30 degrees. You see? So for low frequency, the gain in SNR will be something below 20 dB with 10 sensors. Something below 20 dB. But for higher frequencies, if we go to this higher frequency, you see with the same number of sensors, we can get almost 40 dB gain in SNR. Why is that? Why, when we have higher frequencies, we get better output SNR? Exactly. Because it's more directional. So with the same number of sensors, the beam width of the main beam becomes narrow. So when the frequency is higher, the beam becomes more narrow, so we are able to spatially filter different directions better. So we can increase the output signal to noise ratio. Okay, so we have two options to improve the output signal to noise ratio. Either by separating, so if the desired source of interference come from different direction, have more spatial separation, or when we work with high frequencies, so because with higher frequencies we have better directivity of the array, we can separate, the beam width becomes more narrow, so we can separate them better. Or we can actually increase the array, increase the number of sensors, increase its size, and so on. Okay? And then we get better spatial separation. All of that we see here. Okay? And actually it's just an example of the output SNR, but if you work with other performance measures, you get the same increase or improvement in performance. And it makes sense. So just I wanted to show you that when you look at the results, don't just look at the results. Ask yourself, okay, how does it compare to other situations? What is the dependence on the frequency and why? Does it make sense? If we had lower output SNR for higher frequency, then something is strange, okay? So when you get result, try to think, does it make sense? Why do we get it? Not just because we got it, this is the result and that's it. Because it's very easy in signal processing to make a mistake in the implementation, in the MATLAB code or whatever, how you process. And then you get results And then you say, here are the results. But even though you got it, it doesn't mean that this is what it makes sense. So try to think if it's correct or not, and maybe you expected for different results, and try to explain why you expected for different results. This is especially true with deep learning, because sometimes people get results and they consider that like the ground truth. This is what I got, this is the true performance, which is not. You need to be suspicious about everything. Your work and others' work, try to think if it makes sense or not, and try to challenge to do different experiments. Okay? Let's continue. Now with the Wiener. So the Wiener filter is obtained by minimizing the mean squared error. So we saw that the mean squared error, either the narrowband, okay? So we can work with the narrowband mean squared error, which is summation of two components of the mean squared error. One is related to the distortion. The other is related to the residual noise. So we obtained an expression for this. So this is a scalar function of a vector. And we know how to find the derivative or the gradient of this function with respect to a vector and equate it to 0. And then from that, we find the optimal vector. So if we find it, we see that it looks like this. This is the vector, the optimal vector, which optimizes or minimizes the mean squared error, the narrowband. So by the way, if this filter minimizes the narrowband MSC, what happens with the broadband MSC? What will happen? Does it necessarily also optimizes or minimizes the broadband MSC or not? Yes, yes. Why? That's true. Why? If you said yes, I think you know why. But let's share it with the class. Why is it also optimal for the broadband MSC? Remember, the broadband MSC is summation of the narrowband MSC. So if it's summation, and we optimize each filter for each frequency independently for different frequencies, necessarily we get the minimal broadband MSC. Okay? So the narrowband optimizes not only the narrowband MSC, but also minimizes the broadband MSC. Okay, and then you see that is, okay, so it looks like this. So I want to compare it to the maximum SNR, okay? So first I want to show that this Wiener filter also maximizes the signal to noise ratio, the narrowband output SNR, not the broadband output SNR. Why? Because we saw that looks like that. So it's proportional here. So in order to do that, we will need to show that the Wiener filter is proportional, the narrowband Wiener filter is proportional to this. Phi v minus 1 complex conjugate of the partial coherence between x1 and x. Okay? So let's write it here. So we saw that any filter that is proportional to that maximizes the output SNR. Okay. So if we derive the Wiener filter, we see that it looks like this. So it doesn't look like proportional to phi v minus 1. So it's a question if it maximizes or not. But we will see that we can have different formulation to the Wiener filter. So we will continue. But here it doesn't show like it maximizes the output SNR. But we can define different things. Okay, so first we can show that we can write the Wiener filter like this. This is a different expression based on the normalized coherence matrix. So if we normalize it, so we have something like this. And this is a nice formulation for the Wiener filter because it shows like it's a multiplication of two components. One component, this is the gain that was derived for the Wiener filter when we used single channel. For the single channel Wiener filter, it looks like that. Input SNR divided by 1 plus input SNR. So this is the gain that was obtained for single channel. And this part is a vector that takes into account the spatial filtering. So it looks nice, this kind of observation, how we define this vector, the filtering vector here, Wiener filter, by combining single channel Wiener filter and spatial filter. It's nice. It's nice to see that. Let's continue. Let's see if we can have different expression for this vector and get some insight from these different expressions. So we can write also the Wiener filter like this. Okay? So if I give you different expression, what did I do? Instead of phi x, you see this is very nice, right? It's a very nice way to write different expression for the same filters using your model. So what we did here, you see, we can write that instead of this is complex conjugate, so it looks like that. Okay. If I write it H Wiener F, we can write it as phi x1 F. Okay, I will go backwards. Phi y, the coherence function, minus 1 F, complex conjugate x1 x F. Okay. So instead of this vector, I can write something different. You see, this is the partially normalized coherence function. So I can write it like this. I can write the Wiener filter by the coherence between x without the normalization, because phi x1 multiplied with this partially normalized is simply the coherence between the vector x and x1 complex conjugate. So I can write this vector as the coherence function or correlation function or matrix and multiply it with a vector of 1 and all zeros. I remind you that the vector II is defined as 1, zeros, all zeros of length m. So you see that this correlation matrix, if we multiply it with 1, we have a vector. This is the vector. Okay? which is very nice, because what is phi x? This correlation matrix. What is it? This equals to x multiplied with x h f, expectation. So if we take this matrix and we multiply it with this vector, we get the correlation between the vector x and only the first component, which means that x1 complex conjugate. You see? So we replace this vector with this vector. Matrix multiplied with this vector. Now, instead of phi x, we can write that phi x is phi y minus phi v. So we get this expression. And my question, you are supposed to answer by now. Now you're, after 6 days, you're an expert, right? Okay, so why do we need different expressions for the filters? Why not, if we have one expression, that's it, we use this one. Why do we need other expressions? Can we get different performances with different expressions? Okay? So actually, different expressions will result in different performances. What are the differences? Okay, so when we ask this, think about what do we have. So this expression, this filter depends on phi y minus 1. So we need to invert this matrix, the correlation matrix of the measurements, of these measurements. So we find these correlations, and we need to invert this matrix. Also, we have it here, phi y minus 1. So we need this same information in both expressions. But here, we need the correlation between the vector x and x1. So we need the correlation between any desired component in these sensors compared to the desired signal components in the reference signal. Here, we don't use it. We use the correlation matrix of the noise components. So you see, we use different information. So if you know the exact values of these matrices or vectors, it will result in the same performance if you know exactly, if you obtain the true values of these matrices. But if you estimate it from limited measurements, when you estimate something, so there are different differences between the estimations. Because you can try to estimate this, but you can try to estimate the noise. And then you will get different results because these are estimations. So different estimation processes, when you put it in an algorithm, based on limited data, you will get different results. So pay attention to that. It's important. So sometimes it's important to derive different expressions to see how we can use estimates that we can estimate maybe more reliably. Okay? Maybe we can estimate this better than more accurately than estimating this part. So it's important to have different derivations of estimators, of filters. Okay, let's continue. Now, using Woodbury's identity, we can replace the inverse of this matrix by this expression. If you are not familiar with that, please look at the internet. What is the Woodbury identity, and try to prove this relation. Anyway, if we substitute, instead of phi y minus 1, we put it in the expression, we get a new expression, like this. And we can also rewrite this expression like this and like this. So you see we have different expressions for the Wiener filter, even though it's a vector of length m. Okay, what do we see here? Okay, this is very nice to see it. Okay, here, do you agree that the denominator is a scalar? Scalar, complex value, scalar, right? And here we have a scalar. So if we compare it to the filter that maximizes the signal-to-noise ratio, you see it is proportional to phi v minus 1 complex conjugate of gamma x1x, the covariance function between x1 and x. So you see we got some relationship between the Wiener filter and the maximum output SNR filter, which means that the Wiener filter not only minimizes the narrowband and the broadband output mean squared error, it also maximizes the narrowband output SNR, because it looks like this. From this expression, you couldn't know. But from this expression, you know that. That is all. What do you think? Do we also obtain maximum broadband output SNR using this filter? Yes or no? Yes? Okay, let's think. First, you said yes. More answers? Some yes, some no, or everybody thinks yes? No. Okay. So each one of you maybe try to explain. But before that, I repeat, the Wiener filter minimizes the narrowband MSC, it minimizes, and then it also minimizes the broadband MSC. Why? The reason? Because the broadband MSC equals to summation of all narrowband MSC. That's why if we minimize the narrowband MSC, we also minimize the broadband MSC, because we can work on all frequency independently. What happens with the output SNR? So the output SNR, the broadband output SNR compared to the narrow output SNR, narrowband output SNR. If we compare these two, can we write here equality? No. Therefore, if we maximize, using here, if we maximize the narrowband output SNR using here, using this filter or this filter, still we don't necessarily maximize the broadband output SNR. Okay? In order to maximize the output SNR, you need to choose these values in such a way that the broadband output SNR will be maximized. Here we don't have it. Okay? And actually, using some examples, you can try to find estimates and see and check, verify that you get different results with different expressions. Because sometimes people think, okay, I get a different expression. It's not important. Actually, it's very important, because you can get different estimates from limited data, from real data. And then you get different performances, and you need to think. Just like I talked about single-channel speech enhancement, also I talked about obtaining differences, and we talked about the models and so on. So also here, it's a very, very nice, if you repeat the example that is related to what we show here, and instead of taking these matrices phi x and phi x and phi y and phi v, instead of taking it from the true signals, you take it from noisy measurements, realization of the data. And you try to estimate it. And then you put it in different expressions and see the differences. This is a beautiful exercise. Okay? So try it. So we will continue from here. You deserve a break. 10 minutes. 10 minutes is okay? Okay, so let's have 10 minutes break. We will continue. And noise reduction factor. We just use the Wiener filter. And we can obtain expression also that is desired signal reduction factors. And different expressions for the output SNR that can be achieved, the broadband. So we can show just like what we showed for the time domain, multi-channel time domain, that using the Wiener filter this way, the output SNR will always, the broadband output SNR will always be improved, or at least not smaller than the input SNR. Let's see an example. So if we take the same example that we saw before, sine or cosine, whatever, or cosine signal, sinusoidal signal with a certain amplitude. The frequency is 0.1. We have 500 samples. And theta 0 is 70 degrees, which means that it comes from 70 degrees compared to the array. And the noise comes from the end fire, from this direction. And the thermal noise is very small. It's only 1%. The power of the thermal noise is only 1% compared to the directional noise. So if we use the Wiener filter, we see the gain in SNR, the MSC, the noise reduction factor, and the desired signal reduction factor for different number of sensors. The blue line is for one sensor. Green, 2 sensors, then 5 sensors, then 10 sensors. So you see that the more for a given input SNR, the more sensors that we use, we can have higher noise reduction. We can reduce more noise. Okay, and you see a big jump between 1 and 2 sensors. This is the jump between 1 and 2 sensors. This is jump from 2 to 5 sensors. This is from 5 to 10. The fact that I have a big jump from 1 to 2 sensors, it means that I have significant amount of directional noise, which is true in this example. Okay, because you see that the thermal noise is only 1% of the directional noise. So if I have big reduction or big noise reduction, when I switch, when I add even one more sensor, from 1 I jump to 2, I take 2 sensors, I can reduce a lot of noise because now I can have spatial information. I can separate between the desired source and the undesired interference. Now, if I want to increase the noise reduction, I need to add more. Of course, I need to increase the number of sensors. But the big jump comes from 1 to 2. Afterwards, from 2 to 3, it will be a smaller jump. 3 to 4, so on. Okay. And also, okay, so when I increase the noise reduction, I also increase the output SNR. So the gain in SNR increases when I increase the number of sensors. I also decrease the distortion and decrease the MSC. You see also the decrease in the distortion, there is a big jump when I moved from 1 sensor to 2 sensors. This is a big jump. Because with 1 sensor, I have no spatial information, no spatial filtering. With 2 sensors, even with 2 sensors, I have spatial filtering. So I can suppress a lot of interference, a lot of noise, without sacrificing too much distortion, which is nice. Okay? This tells us that in this example, it's good to use spatial information. Okay? Because it's very important. Spatial information enables you to improve the MSC, to improve the output SNR, and so on, without sacrificing much distortion to the desired signal. But when the noise comes from a certain direction, if I will have noise, thermal noise, or diffuse noise that it comes from all other directions, the amount of performance when we move from 1 sensor to 2 sensors is is not as big as this. Okay, so the jump in performance will be much smaller when we deal with thermal noise or diffuse noise. But when we deal with directional noise sources, directional interferences, there is a big jump, a big gain in performance when we move from a single sensor to more than a single sensor, a few sensors, which means that the array gain it becomes significant. Okay. Now, for this example, we can see our realization. So suppose we measure, this is a noisy measurement. This is the magnitude of the noisy measurement in the reference sensor, Y1. This is the magnitude of Y1 as a function of the frequency. So you see that the desired signal is a certain spike in 0.1 because its frequency is 0.1, and we have the negative value because it's with a certain phase. So this is the noisy measurement. This is the error. This is the difference, the magnitude of the error between X filter desired, it doesn't show here, between X filter desired and X1. Note that the scale is different. Here the scale is between 0 dB and 140 dB. You see, and this is the magnitude of the component. So it's 100 dB. Here, the error, the scale here of the error is between 0 and 20 dB. Okay? So the error is much smaller than the signal component. Okay? So don't think that it's the same scale. So this is the error when we have a single sensor. This is the error when we have two sensors. So you see, this is the same scale from 0 to 20 dB. So you see that by increasing the number of sensors from 1 to 2, the error becomes much smaller. If we increase the number of sensors to 5, you see the error becomes much smaller, which is nice. Okay? If we check the input SNR here is minus 5 dB, and the error, you see here, okay, so the output SNR here with a single sensor, it's 14.2 dB, the output SNR here. If we jump to two sensors, we have a jump from 14.2 dB to 19.2 dB. If we increase the number of sensors to 5, then the output SNR increases to 25.5 dB in this example, for this realization. If you try this, maybe you get a slightly different result because the noise will be different. The noise is random. In this realization, this is the time domain signal in the reference sensor. This is the noisy signal. This is the estimate of the desired signal by using a single sensor. This is using 2 sensors, and this is using 5 sensors. So you see we have much improvement compared to what we learned when we used only a single sensor, because we're able to separate. The separation is 70 degrees. So the desired source and interference come from different directions. So when we have like 5 sensors, we're able to get a very good estimate of the desired signal. But here, we use some information. What is the information that we used? The information that helped us to obtain the correlation matrices, phi x and phi v, okay? But actually, we don't need all the matrix phi x. We just need D the relative transfer function or this correlation vector. We need this correlation vector. And we also need either phi y or phi v. Okay? So it's over there. Okay, so if you don't have this information, actually we assume that we know the direction of the desired source, we know the direction of the interference, and we know also the amount of noise or something like that. So what I suggest you to do is to take this example, and instead of using the information that to get this performance, take some data, realization of data, and try to find whatever you need to find. Try to estimate the filter using measurements, not the model that we used. So this is a good exercise. Okay? So here we have an assignment. Okay? First, the assignment is to derive different expressions that we saw before. So it's a good exercise. And also to generate the figures in example 2, what we just saw, these figures, okay? All these figures. To generate them, I suggest that you generate them, but instead of using the information, the true information, try to estimate it from measurement and see the effect. So this will be assignment number 3. You will have another assignment, 4. Okay? So in this course, we will have 4 assignments. MVDR. Okay, so suppose that we want to do multi-channel signal enhancement using MVDR. The problem of MVDR, so we try to get zero distortion. Zero distortion, or actually, we try to minimize the variance of the residual noise. It's not here. Okay? The variance of the residual noise in the estimate, in Z, subject to distortionless constraint. Okay? I think I showed it when we talked about the linear filter. I think I already talked about it, so I will not repeat, okay? So this is the distortionless constraint, because this enables us to get the X filter desired equal to X1, and this is the variance of the residual noise at the output of the filter. So this is the problem, and to solve this problem, this is the solution. I think we did it a few times, so it should be easy for you to derive this using Lagrange multiplier. Okay? Straightforward. Anybody who didn't do that, please repeat, derive that. So the solution to this problem using Lagrange multiplier, it's straightforward to see that this is the solution. Okay? So this is the MVDR, which is also nice to see. See, it's related, it's proportional to this. So this value, zeta, the weight, this is a scalar. So it's 1 over this. These are the weights. So you see how the MVDR, the Wiener, and maximum SNR are all related. All related for the narrow band. If I will ask you, so we see the MVDR filter maximizes the narrowband output SNR. Does it maximize the broadband output SNR? Of course not. Okay? But it maximizes the narrowband. So it helps us to identify the differences between narrowband and broadband, which are very important. And we can have different expressions for the MVDR, and different expressions will produce different results if we don't use the true matrices, if we use estimates of this information for measurements. So you can try. You can try to see the differences between the expressions. Also in the assignment, try to use different expressions for the winner and see the differences. It's really nice to see. So we can write it in different forms based on measurements or based on, and you see that this is zeta that we can use for, if we use this zeta, it means that it will be NVDR, the narrowband NVDR. Now a question. I have a question for you. Suppose that I find the NVDR which minimizes the distortion for the narrowband. Is it also optimal in the broadband sense? That is also produce minimal distortion? And deliberately I ask you about minimal distortion. Can we get zero distortion for the NVDR? Can we get zero distortion for the narrowband? Zero distortion, it means that this constraint is satisfied. Okay, so if I know the exact information here, if I know this vector, I can design this filter such that the distortion, narrowband distortion, will be zero. So I have no distortion, no narrowband distortion, which means that this filter is optimal in the sense that that we have no narrowband distortion using this filter. Will it also be optimal in the broadband? Suppose that I want that broadband distortion will be zero. Is it also optimal in the sense that the broadband distortion will be zero? The broadband distortion index, for example. Will it be zero? Yes. Why? Okay, but before I ask why, I remind you that if I compare the distortion index, so the distortion index like this, compared to the integral of the narrowband distortion index, this is the narrowband distortion index. So if I take the integral or the summation of the narrowband distortion, can I put here equality? No. But still, if I have zero distortion, so the broadband is also zero distortion. Why? Because the broadband distortion is a superposition with positive weights of the narrowband distortion. Okay? So if I put to zero the distortion index, the narrowband distortion index will be zero, so superposition of zeros also is zero. So the broadband distortion also will be zero. But it also, this is from the expression, but it also makes sense. Because if I don't have any distortion for any frequency, so all the frequencies, so what does it mean? That for all frequencies, I estimate the desired signal component, so I have no distortion, which means that it equals to x1f for all frequencies. So I don't have any broadband signal distortion. Okay? Another question. If the distortion is small for each frequency. So I try to minimize it, but it's not 0. Does it, so suppose that I find a filter that minimizes the distortion for each frequency, but it doesn't obtain 0 distortion. So it's not MVDR, but it minimizes it in some sense. Is it also optimal in the broadband sense? Okay, so in the broadband, you see, the weight, in order to put here equality, the weight that I need to multiply each distortion is weighted by the variance of the desired signal in that frequency. Okay, I can go back to the expression. But here I have certain weights, which means that signal components which are strong, so in those frequencies, I need to minimize more the distortion. So if I want to minimize the broadband distortion, if I don't have 0 distortion in each frequency, but I want to minimize the distortion by some filter, and I want to minimize the broadband, because usually in applications we are interested in the broadband measure. So if I want to minimize the broadband distortion, what I need to do more effort to minimize the distortion in the more significant components, which components where the desired signal is larger. Because if I minimize the distortion in strong signal components, eventually over all frequencies, I have better performance. I don't want to make big effort to minimize the distortion in weak signal components, because it's not, if one is on the account of the other, I want to make most of the effort to minimize the distortion in strong components. Here, I put to 0 the distortion in all components. So of course, I don't have any distortion. I can get, using the MVDR, 0 distortion, also broadband. Okay, and I have different expressions for the MVDR. Here is just use different values. It doesn't really matter. Okay, and what I see here, that using the MVDR, also the output SNR, the broadband output SNR is larger than the input SNR. Of course. Okay. In this example, using the previous example, the same, but I use the MVDR and I compare the gain in SNR using the MVDR, the MMSC, the mean squared error using the MVDR, the noise reduction, and the distortion. So you see, for different number of sensors, blue is 1 sensor, then we have 2 sensors, green, red 5 sensors, and then 10 sensors. So you see that the noise reduction, when we increase the number of sensors, increases. And the gain in SNR also increases because they are together. Distortion, we don't have any distortion because it's designed according to the constraint of 0 distortion. And the MSC, it reduces when we increase the number of sensors for a given input SNR. If I compare the noise reduction using the MVDR, suppose that I have 5 sensors. 5 sensors. This is the red. Okay, 5 sensors. And I compare here the noise reduction. This is the broadband noise reduction factor. If I compare this, MVDR, compared to the Wiener, which one produces more noise reduction factor? Which one reduces, have more noise reduction using the Wiener or the MVDR. Okay, Wiener, okay. Because the Wiener, the noise reduction will be higher, but also the distortion will not be zero. It will be also higher. Okay, so when you want to increase the noise reduction, the Wiener will increase the noise reduction. So you can compare. Then the noise reduction will be higher using the same number of sensors. The same, if you take the same problem and you use Wiener, it will increase the noise reduction, but it will also increase the distortion. So the distortion will not be zero, it will be something larger than zero. If we use the maximum SNR filter, what will happen to the noise reduction compared to MVDR and Wiener? So the maximum SNR, you know, it will suppress more noise, more than the Wiener. So the noise reduction will be even higher, but the distortion will be even higher than the Wiener. Okay, so we know the relations between different filters and the objectives, and we understand what do they do. Okay, the MVDR, we have signal subspace. It doesn't distort this signal subspace. So the amount of noise that is reduced or suppressed is just in the noise-only subspace. That's why it's limited in the amount of noise that it can reduce. The Wiener suppresses more noise, and it introduces in the signal subspace some distortion. The maximum SNR filter, actually, it can remove all components, and it will keep only one component with the highest SNR. So it will produce the maximum amount of noise reduction, but the maximum amount of distortion compared to these filters. Trade-off. So we saw that the MSE can be written in such a way that it contains two components, so we can add here a parameter mu, which will control the trade-off between noise reduction and signal distortion, or to put it like this. So it went back. Okay. So we can solve this problem with the Lagrange multiplier mu. And we have nice formulation. So we have this expression, but we also have other expressions, which are very nice. Because what we see here in this expression with the trade-off, that if mu equals to 1, okay, this is simple. If mu equals to 1, what do we get? The Wiener filter, right. If mu equals to 0, what do we get? MVDR. Which is nice. So we see the relations between the trade-off filter, MVDR, and the Wiener filter. Okay, so for mu equals to 1, we have the Wiener. Mu equals to 0, the MVDR. Mu larger than 1 results in a filter with more noise suppression. The noise reduction factor will be higher, but the distortion will be higher. Mu smaller than 1, we have less noise reduction, but also less signal distortion. And of course, all comes with a price, so we have some relations between the output SNR, the different filters. It also, we can prove, it's nice to prove, because everything that we do here with the narrowband, but we can prove that the output SNR, the broadband output SNR, is an increasing function of mu, which is nice. Something that you need to prove, to think about it. Some things are also maybe simple, some are less simple, but it's possible to prove that. So intuitively, this is very important because sometimes you want to show that, you see, when we derive the trade-off filter, we derive it in the narrowband sense. Okay? And we try, so this gives us some trade-off between noise reduction and signal distortion for the narrowband. But you know that the output SNR is not an integral of the narrowband output SNR. So to show that this is the output, the broadband output SNR is an increasing function of mu, something nice. Okay? So sometimes it gives us insight to show that this parameter mu, of course, we can choose different mu for different frequencies. Here I can put mu, which is constant over all frequencies. But I can change it. For each frequency, I can change it. But if I use a constant mu, then the broadband output SNR will be an increasing function of mu, which is nice. Nice to show. And then I can ask you, does it make sense to change mu for each frequency? Does it make sense? Maybe I will choose for each frequency a different mu. Depends on what I want to achieve. Okay, so this is a question. Let's continue. See, sometimes I ask you questions, I don't give you answer. I want you to think. The distortion index, you see the output SNR, is an increasing function of mu. The broadband desired signal distortion index is an increasing function of the parameter mu, which also is something nice. So both are increasing function of mu. So when I increase mu, if mu is constant, independent of f, mu is constant, I increase the output SNR, I increase distortion. So this gives me a nice trade-off. When it is an increasing function, I didn't say if it's a linear increasing function. Maybe it's a nonlinear. And maybe I can find a good trade-off. How one is increasing and how the other one is increasing. Maybe one is increasing quickly, the other one is increasing slowly in some regions of mu. So maybe I can choose a good value of mu. All these are interesting questions. So we can find for certain applications and certain type of signals, different types of environments, maybe these increasing functions look differently. And then we have a smart way to choose these parameters. And maybe to each frequency choose a different value. Okay? We have some flexibility. When you have a flexibility, always try to exploit this flexibility. Okay, and of course, the output SNR with the trade-off is at least as the input SNR. So you get broadband improvement of the input of the signal-to-noise ratio using the trade-off for any mu larger or equal to 0. When do you have here equality? Do you have here some equality? When? When the broadband output SNR will be equal to the broadband input SNR using the trade-off. What do you think? Can you answer this question? So my question is, when do you think we cannot improve the signal-to-noise ratio? Under which conditions? What? When the input SNR is high, but it's not infinity, okay, so if we don't have noise, we cannot improve. But when the input SNR is high, it means that we still can improve, but the improvement will be small. But I'm talking that you cannot improve anything for a certain input SNR. It doesn't really matter what is the input SNR. Under which conditions you cannot improve the input SNR? Of course, for noisy measurement. If what? Okay, so if it comes from the same directions, so it means if you don't have thermal noise, you have interference, and it comes from the same direction. So if you use multiple sensors, it's similar like you use one sensor. Okay? But I don't want to talk about the environment, the number of sensors, and so on. I just want to ask you what kind of filter reduces the least amount of noise, or which filter obtains the minimal gain in SNR. The MVDR, okay? Okay, so the MVDR, it's the most limited in the amount of noise that it reduces, okay? The MVDR. Why? Because we don't want to distort the signal. So we said that with the MVDR is it's obtained when mu equals to 0, right? So with the MVDR, do we always get improvement of the output SNR, or sometimes we don't get improvement? What are the differences? Under which conditions we improve the output SNR? Under which conditions we cannot improve the output SNR using the MVDR? Think about the noise subspace. Exactly, exactly. So if the noise subspace is empty, the signal subspace, the signal plus noise subspace, spans all the space. So we don't have noise-only subspace. Then we cannot improve the output SNR using MVDR. So here we have inequality when mu equals to 0, and when the signal subspace, which means that phi x f is full length, the rank is m for all frequencies, which means that we cannot reduce noise. It's full rank, okay, for all frequencies, with any frequency. If we have some frequency that we can reduce noise, then we improve. We improve, so we get higher output SNR than the input SNR, broadband, okay? Questions? Okay. And you have, of course, these relations with, this is what we just talked about, the relations between different filters with respect to the different filters with respect to the output SNR, and what we pay for that with the distortion. Example. Now we use the trade-off filter with different values of mu. With different values of mu. The blue line is mu equals to 0.5. The green, mu equals to 1. Then the red is mu equals to 2. And the light blue is mu equals to 5. So we see that for a given input SNR, the noise reduction, the broadband noise reduction factor, when we increase mu, the noise reduction increases. So we reduce more noise when we increase mu. The distortion also is an increasing function of mu. See, the output SNR is an increasing function of mu. The distortion index and the desired signal reduction factor are decreasing function of mu. It's nice. So we can control mu, and for different environments, different type of signal and so on, we can find the optimal values of mu. LCMV. Okay, so maybe I will give you a break, the tea break, just because this and the next are very important, and I want you to be focused. The LCMV, because it's very important, and the generalized side lobe counselor. The last two filters that I'm going to talk in the next hour. So I want you to be focused because it's slightly, so it's more new material that I want to cover compared to, because the other things, Wiener and MVDR trade-off, we talked about single channel, multi-channel in the time, so you're familiar. LCMV and GSC, generalized side lobe counselor, you are less familiar, okay? So I want you to focus on that and to cover that in the next hour, okay? So I have a tea break, but not too long, okay? So 10 minutes is okay? 10 minutes. So now it's 4:10, let's say. Okay, can we continue? Okay, so before we continue with the LCMV, I want to show you a short clip about the cocktail party effect. So cocktail party effect is actually when we are able, when there are many people around us, we're able to concentrate on a specific speaker. And with signal processing, it was challenging for a long time. Now it's possible to do some, there are significant progress in this area. So I want you to see some video clip.
What is the cocktail party effect?
It's this phenomenon where in the midst of a noisy cocktail party, any kind of noisy sporting event or newsroom, we're still able to focus in on the one conversation we want to hear and somehow tune out everything else.
And how can, now researchers, neuroscientists are very interested in this. Why is that? Why do they want to know where this ability comes from?
It's part of this whole phenomenon of selective attention, wherein the human brain can only really focus in intensely on one thing at a time. And this is a survival skill. You know, we're constantly bombarded by all this visual and auditory stimulation. We couldn't survive unless we could focus in like this, but we can also only really focus on one thing at a time. And that's what's at issue in distracted driving and all kinds of other limitations of multitasking.
Are there people who, is there like a small percentage of people who actually have sort of a super ability to focus on more than one thing, or is that a myth?
Yes, researchers at the University of Utah have found some of these people in the course of their other research. They think it's about 2% of the population. The real problem is that most of us think we can do that, and that can have some disastrous consequences.
Okay. Okay, so we want to move on to LCMV. So let's explain what is LCMV, and I will give you some motivation. And the motivation will come from what we talked about MVDR. So you can view that as an extension of the MVDR, minimum variance distortionless response. So suppose that we have an array of sensors like this. And suppose that we have desired source that comes from a certain direction. And we have undesired source that comes from another direction. And in addition, we have some other noise components. Maybe we have a few directional interferences. What we can do? Okay, so first what we can do is we work with the MVDR. So the MVDR is defined as minimization of the variance of the noise at the output of the filter, okay? So we find the filter for each frequency. Okay, so we always work for each frequency in this area. So for each frequency, we find the filter that minimizes the variance of the residual noise at the output of the filter, which is H transpose conjugate VV H, subject to distortionless constraint. Because we want that for each frequency, we don't have any distortion of the desired signal. Which means that when we estimate the desired signal, which is an estimate of X1F, we have two components. One is X filter desired plus V residual noise. So if we want that the filter desired will be equal to the original signal, this is the signal that is measured in the reference sensor, which is X1F plus V1F. If we want that X filter desired will be X1, so we don't have any distortion, we need the distortionless constraint, which we showed that it's similar to H transpose conjugate D equals to 1. This is the distortionless constraint. Because if we satisfy this, then we don't have distortion of the signal in the frequency F. Okay. So what do we do next? And then with MVDR, we can derive it, we showed it, and so on. So if for the distortionless constraint, see, we can find the solution, but with distortionless constraint, we use this propagation factor or steering vector for the desired signal. Now, suppose that I know that I have undesired interference, and I know the propagation vector or steering vector of this interference signal. So I can use that as well, because here I try to minimize the amount of noise. But maybe I can now formulate a new problem like this. Let's minimize the total variance of the noise, okay? But before that, okay, I will write it like this. So you know that I can write the vector of measurements in the vector F, okay, for the frequency F, I can write it as X1F dF plus the noise vectors in all sensors. We saw that. And also we saw that we can separate this noise into two components. One component is the coherence noise, and the other component is the incoherence noise. So I can write it as X1F dF plus the noise, which is correlated with the noise in the reference sensor. I can write it as V1F multiplied with the coherence function, the partially normalized coherence function between V1 and V, just like we did here. This is the same. You see, this one equals to the coherence function, the partially normalized coherence function between X1 and X. So I can do the same for the noise. But then I have an additional component, which is the incoherent noise. Because generally, we don't have just noise source, one interference. We have additional sources, maybe the thermal noise, diffuse noise, so on. So I can add here the remaining part of the noise, which I will call it, let's call it V prime, F. This part will be the part of the noise that is incoherent or uncorrelated with the noise in the reference sensor. This is something that we did, we showed in the formulation of the problem. Questions so far? Okay. So what I can do now, I can define a new problem. Suppose that I know this vector. For the MVDR, I didn't use this vector. Suppose that I know additional information. I know to estimate this vector. I know to separate the noise sources, the noise that are measured in the array, into two components. One component which is correlated with the noise in the reference sensors. The other components are uncorrelated. Suppose that I know to separate this. Does it help? Okay, so let's define now another problem to find an optimal filter, which will be like this. Okay, I will remove this because I want this space. You know, in our university, we have like larger than this, 3. So we can continue. We don't delete. Okay, so maybe next time, maybe we can have 2. So I don't need to delete, and I can keep some of the things. Anyway. Okay, but even 2 like this also may be useful sometimes. Okay, but we manage with what we have. Okay, so I can define a new problem now. Let's define a new problem. Let's minimize the variance of the noise, okay, the total variance. Maybe even I will write it like this. Let's minimize this variance. Or, you know what? I will write it like this. Okay, so the total, because I don't want to confuse you, I want to keep that simple. So let's minimize the noise, just like we did for the MVDR. So I minimize the variance of the noise, of the residual noise at the output of the filter, okay? But subject to 2 constraints. One constraint, subject to 2 constraints. One constraint is the distortionless response. Another constraint will be H transpose conjugate, F, complex conjugate of gamma, the steering vector of the coherent noise, will be 0. Because I assume I can estimate this vector. So I can formulate this problem. Can I solve this problem? Yes. Suppose that I know how to solve it. Actually, when I have 2 constraints, so I have Lagrange multipliers, 2 Lagrange multipliers for the 2, and I can solve this problem. So I can find a solution. So the solution to this problem is called LCMV, linearly constrained minimum variance. Because linearly constrained, so it's minimum variance. Minimum variance. So it's minimum variance, like the MVDR, minimum variance. But we have 2 linear constraints, so we have more than one. So it's kind of extension of the MVDR. Any questions? So it's important first to understand the problem, the mathematics behind it. Now let's think beyond that. If you have questions, now is the time. If you don't understand, okay. So we see this formulation. So what did we do here? Did we do here? Suppose that we have like interference from a certain direction, and we know its direction, we know its relative transfer function estimate, its propagation vector. We know this. We can put a null towards this direction and suppress it completely. So when we have here the minimum variance, it will minimize the variance of this residual part. Okay? So I can write it in a more general way, which I will do soon. But first, I want to ask you a question. Suppose that we compare the output SNR, narrowband output SNR, that is obtained, the output SNR that is obtained using the MVDR compared to the LCMV. With which method, which filter will we obtain higher output SNR? Okay, think. MVDR, what is MVDR? MVDR, we have signal subspace, and which contains signal subspace, signal plus noise subspace, and noise subspace. So in the signal plus noise and subspace, we don't touch it. We keep it as is. In the noise subspace, we suppress all noise. We minimize. So we put to zero all that noise in the noise subspace. Okay? So we have in two different subspaces. One is distortionless, and we try to minimize. And then if we write the output SNR using this MVDR, it will be higher than the input SNR. So this will be equal to x1, and this one we try to minimize the variance of this one. Okay? Now with the LCMV, what we try to do, we add another constraint here, this one. So the interference that comes from this direction, because we know this, its propagation vector, it will not be measured in the residual noise. So it will be null. No contribution in this estimate. And then we try to minimize the variance of the residual noise under this constraint. So the signal subspace, we don't touch it. You see, signal subspace, we don't touch it. But within the noise subspace, we add additional constraint that the noise, the coherent noise, will be zero at the output, and we try to minimize its variance under that constraint. Okay? Now the question is, with which method will we be able to reduce more noise? MVDR or LCMV? Okay. Everybody says, almost everybody. I didn't hear MVDR. So this is actually intuitively, when people say an answer, when I ask this question, people will say LCMV. You know why? Why your answer is like this? Because what did you assume? You made an assumption. What was the assumption? That actually it's because I showed you all these examples, all the examples that we showed in the performance in this chapter are with that the directional noise is the most significant. We showed that the noise is composed of directional interference, which is significant, and very small amount, maybe 1%, of thermal noise. So you say that if we put the directional noise, the coherent noise, we put it to 0, maybe it suppresses more noise, right? So even under these conditions, the NVDR suppresses more noise. Why? So this is a simple answer. But I knew that you may answer that LCMV, because this is the intuition. But I want, exactly. When you compare the output SNR, so the output SNR is the variance of this, divided by the variance of the residual noise. So in both cases, the NVDR and LCMV, this part is the same. It's X1 because it's distortionless response. Both are distortionless responses. So this part is the same. So the variance of X1, the X filter desired equals to the variance of X1, the same. The only difference is the variance of the residual noise. So here with the NVDR, I minimize the variance of the residual noise without any additional constraint. So necessarily, it will be lower when I add additional constraint. You know, in optimization, whenever you have additional constraints, the performance is lower because you have additional constraints. Okay, so first, from a mathematical point of view, the output SNR with the NVDR is higher than the output SNR with the LCMV. All agree? Or someone doesn't agree? We will explain until everybody agrees. Okay, so we have additional constraint. So this constraint, what do we achieve with this constraint? What do we achieve? We achieve that the coherent noise, the interference, is 0 at the output of the filter. But the variance of the residual noise with this constraint, maybe it will not as good as the NVDR. Think about, suppose that we have noise like this, but this noise is very weak, very weak. And most of the noise comes from alternative, other types of noises. So if we, here with the NVDR, we don't care. We just care about the variance, the power. So we care about the power, the variance of the noise, and we minimize it. So we get the maximum amount of output SNR, the narrowband, okay? So maximum noise reduction for this frequency. With the LCMV, we have the constraint that this contribution will be 0. So we can, even though it's very weak, we put that constraint, and then we are restricted how much noise we can reduce. And maybe the other noise is significantly more significant than this part. Understood? Okay. Any questions? Okay. If you don't have a question, I will ask a question. Okay? So we see, yes, somebody wants to ask. the noise, we can always split it into two components like that, always. Because one component is coherent with V1, the other component is the difference, the remaining. We always can do that. Even if we have combination of many types of noises, we can always do that. Because here we take each part of the noise, the part that is coherent with V1 and the part which is incoherent. We can always do that. Any other question? What is what? Okay, this is what I want. So you asked the question that I wanted to ask. So it's a very good question. You know, sometimes we say it's a very good question because we want to the next slide, or that is what I want to address. Exactly this question. The same question? Okay. What? So you tell me, if this is the same as this, what does it mean? It's on configuration of the array, but the array is the same for these two components. So you have an array. If D equals to this, what does it mean? It means that the sources, if they are both far-field, they come from the same direction. If they are near-field, they are in the same position. Because the steering vector, propagation factor, it depends on the correlation, including all the reflections. So if it's far-field, the desired source and the coherent noise come from the same direction. Okay? So obviously, if they come from the same direction, we are limited in there. We cannot reduce one by keeping the other. Okay? You see, these two constraints, if this equals to this, we cannot satisfy both. We can satisfy both if they are different. They come from different directions. Okay. So let's talk about the first question. The first question that you ask. So if the output SNR that is achieved with the MVDR is higher than the LCMV, what is the advantage of using LCMV? Why do we need LCMV? Under which circumstances? When there is advantage of using LCMV compared to MVDR? This is your question, right? Very good question. Let's think. What do you think? Let's think about the answer. Think about what or under which conditions it's better to use LCMV than MVDR. So this question, we can put it on the quiz. Actually, it's a very nice question. You see, I can tell you that people that work on array signal processing, I met people that work maybe sometimes a few years on array signal processing, and they don't understand this. If you ask them, they don't understand this difference between LCMV and MVDR. They think they know, but when you ask them, they say the wrong answer. They think LCMV, it makes sense that it's better. But when something is better, you need to understand when is it better? Under which conditions? Okay. So when we compare something, we see that we compare the MVDR and LCMV, and if the objective is maximum output SNR, or equivalently, if the objective is to reduce noise, the power of noise, then always MVDR will be better. So LCMV is better when we talk about different objective. So the objective is not to reduce more power of the noise. Different objective. Okay, so what can be the objective? I'll give you an example. Sometimes, so if we talk about audio, but it's similar, I can give you many other examples. Not audio. I can give you underwater communication, radar. So I can give you a few examples. Let's start with audio. Do you agree that if I have non-stationary interference, even if it's weak, it's more disturbing than white noise, which is stationary? We know that when we listen to a signal, you can do it yourself. If you work on the speech enhancement example, assignments, if you worked on that, you could record yourself and you could add noise. So if you add white noise, white Gaussian noise or something like that, it's less disturbing. It's just we are tired when we try to listen to understand what somebody says, and there is like fan noise, air conditioner noise, some stationary car noise, even airplane noise. You see, sometimes you have a long flight on the airplane. There is the noise is stationary. And after maybe 10 hours, if you don't put earplugs, you feel headache. And you don't understand. Why do I have headache? Because you hear noise all the way, 10 hours. Noise, so you will have headache. You know? So people get used to stationary noise. They don't think it's disturbing so much. That's why they don't put earplugs. But it's not good for listening, and it makes the brain tired. And also, if you try to listen with, if you are in an environment, you try to listen to see a movie or to a class, Zoom, and you have air conditioner noise. Or during the night, you put the air conditioner and fan, and you have noise, so it affects the brain. That's why I recommend to put earplugs if you have such background, even stationary noise. But if I put some non-stationary noise in the background, you immediately feel, oh, it's disturbing. Okay? So suppose that here we have some directional noise or coherent noise, which is non-stationary. Like I put something like this. So if I continue the lecture like this, it's very disturbing. But the amount of energy of this signal is very low, right? Because the amount of energy is limited in the time, by time samples. So the amount of energy, something like this, is very low. So maybe this has very low energy. So if I use the MVDR, what does it try to do? To minimize the power of the noise, the variance of the residual noise. So it will find filter that minimizes this variance, the power of the residual noise. So it will try to minimize the amount of energy. If we have stationary noise, it will put more effort to minimize the more powerful noise, which is the stationary. Because this has very low energy, but it's very disturbing. So what do we need to do? Is to put here another constraint that even though this has low energy, we want to suppress the contribution of this noise source because it's very disturbing. Not because of the energy, because it's disturbing, for example, if it's non-stationary. Okay? So this is the advantage of using LCMV. So if we have weak signal, weak interference noise, that the significance of the interference, it's not because it's high power, but because it's disturbing more at the output based on some non-stationarity or other features that make it, at the output, make it more significant. So we want to give it more significance, more weight, so that we reduce that part at the output. How do we do that? We add a constraint on this interference. So when we add constraint on this interference, even though it's, in terms of power, it's weak. So we limit how much noise, the variance of the noise we can reduce. But we are willing to pay that. We're willing to sacrifice the variance of the residual noise because this part is important to us. So we added a constraint because we want to reduce this type of noise. Okay, and I can give you another example. Radar. Suppose that I try to detect the distance of a target. Where is the target? The range, direction, velocity, and so on. And suppose that I have an interference. And maybe the interference in terms of power is not strong, but it interferes with the signal that I send. Somehow, okay? Maybe they try deliberately, maybe they don't try, but because maybe they send another signal from another place and so on, or I have some interference, even weak interference from a certain direction. And I want to suppress that, even though it's a weak signal. So I can add a constraint to suppress source that comes from that direction in order to achieve a better signal that will enable me to find the range, direction of the target, and so on. And I can give you additional examples, but there is no need. Now you understand. Any questions? Okay. So now that you understand that, I suggest that once you meet somebody that works in array signal processing, try to ask him this question. See what the answer. Many people, they don't understand it somehow. I don't know why. Because sometimes it's confusing, or they're not familiar with the mathematics and the applications. But this is, and I can give additional examples, but that's enough for now. Maybe you can give other examples in your presentations, which you start today, right? Today at 5:30, you start your presentation. Okay. Now, after we discuss this, actually, this is what I wanted. This is the most important thing regarding the LCMV and the relation between LCMV and MVDR. Because after we define this mathematics and we understand it, that's it. You understand. All the mathematics is very simple because we add two constraints. So how do we do that? The mathematics behind it is very simple. So we define a matrix C. You see the column, the first column is the partially normalized coherence function between x1 and x. The second column is the partially normalized coherence between v1 and v. So if we define the constraint like this, it's the same as these two constraints. See, it's the same. So it's very useful to write the constraint such that we have constraint, the matrix of the constraint, you see, C. So the matrix C actually contains coherence functions or propagation vectors. So in this case, this matrix for each frequency is the size of m by 2. Sometimes we can add more constraints. That's why it's called linearly constrained minimum variance. So the constraint matrix is like this. So you see, the first one is actually the MVDR. If we have more constraints, we can add additional constraints. So we put 1 here for this part and 0 for the coherent noise. Now, to solve this problem, so we can define that the LCMV filter is the argument that minimizes the variance of the noise. Actually, here, instead of variance of the noise, I can put phi y instead of phi v. Do you agree or not? The same. Why is it the same? Subject to the constraint. So here, I can put phi y. Why is it true instead of phi v? Yes. So if we have the constraint of distortionless response, so actually phi y equals, you see, if I write it like this, okay, y equals to x, okay, plus noise. So if here this part will remain the same, we constrict it. So of course, when we have phi y, it equals to phi x plus the phi v x. Okay? But phi x, what is phi x? Okay, I'm going to remove this. We know that this part is x1f multiplied with df. Okay? So phi xf equals to phi x1f, which is a scalar, df dhf. Agree? So if we have over there H phi y H, okay? So it's this plus this. So what happens? So I can write it as H transpose conjugate multiplied with phi x, which is phi x1 H f df dhf hf. This part is multiplied with phi x plus h hf phi v f h. Agree? Okay? So I used phi y, summation of these two, and I used that. So I put that. Okay? What is this? Under the constraint of the MVDR, this equals to 1. So this is also 1. So when I try to minimize this, okay, so assuming So we have, and the variance of the input is the same. This is independent of H, right? Because this is the input. This is the signal that is received in the single sensor. So it's not independent of H. So if I want to find H that minimizes this, is the same as finding H that minimizes this. Okay? Okay. That's why we wrote here H, phi y, which is the same. By the way, when we minimize the power, this is very nice to write it like this, because when we minimize the power of y, no? So it's just like finding something like that. Sometimes in the literature we call it differently. Instead of MVDR, minimum variance distortionless response, which is defined here with phi v, we call this minimum power distortionless response. So we give it a different name. Sometimes people call both MVDR, but sometimes people call to this problem MPDR. So the question is, why to call it different names if it's the same? If you have two different names for the same thing, does it make sense? What? Exactly. Okay, so the answer is that if we estimate phi y or we estimate phi v, the results are different. If it's true, if it's the correct one, it's the same. MVDR and MPDR, they are the same. But if we estimate the correlation matrix of y or the correlation matrix of v, it's a different result. Okay? Good answer. So you listen. You understand. Okay? These small things are very important because it's relevant not only to this material, it's relevant to whatever you do. Understand the things. So we get different expressions, but the results will be different if we have estimates of these values, these matrices. So if we solve this problem, we can solve, we have this solution. So of course, if we can replace, instead of phi y, we can put phi v. We will get, in theory, it's the same LCMV, but instead of minimum variance, if I put here y, we can call it LCMP. Linearly constrained minimum power. In theory, it's the same. In practice, it's not the same. Okay? Let's continue. So now that you understand the most important things, we can skip some of the things. Okay? This, I talked about it. I talked that if we compare the LCMV, the noise reduction with LCMV is less than the noise reduction with MVDR. This is exactly what we talked. And we explained it. And of course, the noise reduction with MVDR is less than Wiener. Okay? And let's see an example. So we have the same example with the number of sensors is 5. And here we see the performances, the gain in SNR, the MST, the noise reduction, and the signal distortion with the LCMV when we have different parameter alpha, and alpha is the ratio. Okay, so alpha is the ratio between the variance of the thermal noise and the variance of the directional noise. Okay, and then we compare the amount of noise reduction. So what do you think? If I just want to compare the amount of noise reduction. So you know that the amount of noise reduction when I add constraint. So I added this constraint. This constraint. And then I try to minimize the noise. So what I said, that if the directional noise is very strong in terms of power, so the LCMV will suppress more noise, because we try to eliminate this noise completely. So it makes sense. So the more that sigma u squared, that the variance of the directional noise, the more that this is more significant, if this is very significant, then the noise reduction will be higher using the LCMV. Okay? So if alpha goes up, it means that the variance of the directional noise is smaller. So if alpha goes up, it means that this part is weak. So the ability of the LCMV to reduce noise is reduced, because we try to eliminate something which is weak. So using the LCMV, so if alpha is large, it means that we try to put a constraint on a weak component. So it means that the noise reduction that we reduce with the LCMV is going down, and vice versa. But still, even though the noise reduction goes down, we are motivated to use the LCMV in case that this weak component is disturbing, not because it's strong, because it has some characteristics or some features that disturb us in the output of the filter. So if we see that, let's see that in this example. So here, the blue line is alpha equals to 0.1, 0.03. And then we have 0.1, the green, and 0.3, and then 1. So when we increase alpha, the noise reduction reduces. So we have less noise reduction. Less noise reduction, less output SNR. And of course, the distortion is 0. Why the distortion is 0? Because of this constraint. LCMV also, no distortion. Distortion is 0. But if the power of this is smaller, in terms of noise reduction, we have less noise reduction. But still, it might be better than the MVDR, because we don't care only on the amount of noise reduction. We care about the characteristic. So sometimes low power noise makes a big difference. We don't want it at the output. And then we will use LCMV instead of MVDR. Okay, and then we can also extend it to additional constraint. So this is the constraint. So we can write it in this way. So you can have additional constraints. Sometimes we want, sometimes, for example, we add constraints based on some directions that maybe we don't have. We have interferences from certain directions, but we don't have them all the time. sometimes we have from this direction, sometimes from this direction, sometimes from this direction. But we don't have detector for these interferences. So we put null to this direction and to other direction, even though we don't detect them. Because sometimes they appear, sometimes they disappear. Somebody tries to interfere with us. So once we measure the correlation, the steering vectors of these interferences, we can add more constraints to put to 0. Or maybe not 0, we can put some suppression to this direction. So the more constraints that we put, that we add, the less noise that we can reduce. The less noise in terms of power. But still, maybe this is something that we are desired to sacrifice. So we sacrifice the amount of noise reduction, but we want to suppress some directions which are interferences, even though there is not much power there. Sometimes they appear, sometimes they disappear, things like that. And we can solve this general formulation, you see, and this is the solution. So of course, if we have only the one constraint, the distortionless constraint, this is the MVDR. And here we have a list of what we learned so far. Wiener, maximum SNR, Wiener, MVDR, trade-off, LCMV. We see the relations between them. Very beautiful to see all these relations and their performances and how they relate to each other. Any questions? Okay. So this part, I will talk, it will take more time, so I will talk about it tomorrow. So I will skip it for now, but I want you to understand, because generalized side lobe counselor, it's very important, and it's related, it's an implementation, a different implementation of the LCMV. So instead of a direct solution to the LCMV, what we showed here, this is a direct solution to the LCMV. So instead of finding a solution to this and implement it using like this, you see this is the inverse of the matrix and so on, of this phi y, we will implement it differently. But it's important, and we have 10 minutes, so I don't want to talk about it now. I will talk about tomorrow. I want to talk about something else, which 10 minutes will, I have 10 minutes, right? Or maybe finished, I don't know. Finished or 10 minutes? Maybe 5 minutes is okay? Okay. So I will talk about implementation in the STFT, okay? So for tomorrow, I want you to read the slides about the LCMV. You know, because I will give you a different way to have a solution which is relevant to implementation. And I want to talk about it. It will take me more time, so I want to talk about it in length tomorrow. For now, I want just to give you implementation with the STFT. So we talked about implementation in the STFT domain for single channel. So we also have implementation in the STFT domain for multi-channel. How do we do that? We take the short-time Fourier transform of the signals for each sensor, and then we work on each frequency bin separately. And then all the filters that we saw before, we just use them in the STFT domain. So it's very similar to what we did with single channel, when we do it with multi-channel. So we define for each frequency bin, we take the STFT, okay, this is the STFT. And then for each frequency, this is just the STFT implementation, for each sensor. And then for each STFT, we write it like this. So instead of frequency, we have time frequency bin. And then we find a filter that is applied for each frequency beam, okay, along the time. So the filter will look like this. It's very easy. That's why I don't want to waste time on this. So we estimate each frequency, so each frequency beam, by applying the filter. And the filter is the same as just what we found in the frequency domain. So it's equivalent. So if you understand what we did with the single channel STFT domain compared to frequency domain, so it's the same what we do here. We find for each frequency beam a filter that is applied to the frequency beam in the STFT domain. Very similar. And then I can give you also an example with speech signal, just like we did with single channel. So if I show this example, that we have speech plus noise. So if we work with single channel, this is the result of speech enhancement with single channel. What you already did. You worked on that with a single channel. This is the single channel. If instead of single channel, I add more sensors, this is with 2 sensors, this is with 5 sensors. So you see, I improve the speech enhancement. I improve the output SNR. So you can take the code, the MATLAB code for these figures, for this example. You can play with it. Multi-channel speech enhancement with multiple sensors. So it's a very nice example. If you have time, go through, play with it, compare to the single channel. Okay? But there is not much to talk about it because it's very simple. It's just, instead of the Fourier transform, we work in the STFT domain. And we find for each frequency beam a filter. Okay? So tomorrow we'll talk about GSC, Generalized Side Lobe Counselor, and to see how it relates to LCMV, which is a topic by itself. We will talk about it. Okay? So I will assume that you understand LCMV, and we will show another way to derive the LCMV using GSC structure, which is very important because you find it a lot in the literature, both the MVDR and the LCMV and the GSC. Okay? Any questions? Okay, so we have a few minutes break, and then it's your presentations, right? Okay. Okay, so we have like a few minutes.
good evening, everyone. So myself Venkatesh, I'm coming from IIT Hyderabad, and my team member Dr. R. Kannan, he is from National Institute of Ocean Technology, and on behalf of my team, I'll be presenting the slides, and we'll be presenting on adaptive neural networks for single channel speech enhancement. So I'll be talking about neural networks mostly. So please bear with me if you don't know like deep learning and all. Okay. So this will be like overview kind of thing. I will not be talking about any architecture or anything. So it's just like the idea that I'm trying to present, and like how we can. So mostly I'll present an idea from image processing and how I wanted to take it to speech. Okay. So that's my goal. So yeah. Coming to the motivation, so like we are trying to look at the adaptive neural networks for a single channel speech enhancement. I mean the adaptive in the sense we wanted to change the neural network based on the input. For example, if we see the current neural networks, once we train the neural network, we keep the network fixed, and for any kind of input we use the same network to enhance the signal, right? So like if like we trained on a certain amount of data, so based on the availability of data, we trained on certain amount of data. And we will not be able to cover all the data that we have in the world, right? So we will be missing some of the data, and like if we wanted to test it on a particular environment, which we haven't trained, right? So if we wanted to test it on that particular environment, the model may not perform well, okay? So it may not perform well, it only performs better on the data that we have trained it on, right? So here we are trying to address the issue where we wanted to like change the model itself based on the input signal so that it performs better on any testing environment. Okay, so if we change the testing environment, we wanted to change the model itself. So the main motivation is coming from the adaptive filters. For example, if we take the steepest descent adaptive filter, the weights that we are using, it depends on the input. Okay, so like we change the adaptive filter at each time instant, and at each time instant, the filter weights are dependent on the input. Right. So if we see the weight update equation, so like the weights at the next time step, it is dependent on the current time step weights and also the input, right? So if the input is more correlated with the noise, I mean the error, then we have some information about the input in the error, and so we use the correlation, like the weight update will be directly proportional to the correlation of this input and the error. So when we don't have like any more information of the input in the error signal, we stop updating the weights. Okay, so that is the idea of steepest descent adaptive filter. And the main takeaway from this adaptive filter is that we wanted, like we are changing the weights depending on the input. So why can't we do it for neural networks also, right? So our idea is like current neural network models where the input is S of n, noise is speech signal, and d hat of n is the enhanced signal. So we use a fixed f, which is representing a neural network here, and we wanted to change it based on the input. So now I'm making it a function of s, right? So that is the change that we wanted to make. And like how we can do this? That is the question that we are asking. And one way to do this that I will be discussing here is test time training. Okay, so during testing we will train the network again. Okay, so we change the parameters. So how many parameters to change, how to change the parameters, those are the things that I am going to discuss about in this particular presentation. Okay, and like this particular paper that has been published in like PMLR 2020, which is one of like prominent conference on like the machine learning. So we'll be discussing this particular paper, and we'll also like end it with some remarks on how we can use this for speech enhancement. Right. So yeah. So coming to the test time training. So the main idea is that like the test sample that we are having from a test environment, it gives us a hint about like what the test environment is. Right. So single test sample, which is sample from a like the random process, it gives us a hint about the test environment. So now we wanted to make use of this test environment, I mean the sample function from the test environment to update the network. Right. So the model is no more fixed. We are changing the model based on the input, right? So we are changing it at the testing time. So like any neural network model, once we train it, we keep it fixed, but here we are changing it at the test time. Okay, so like like how we can change the network at the test time, right? So like, for example, if you consider any neural network which is trained in a supervised manner, where we have targets for particular inputs, so we train it by computing the loss and backpropagating the gradients, right? So, but for test sample, we will not be having any target, right? So how we can compute the loss and how we can backpropagate the gradients? So that is the question. So like, to put it in simple words, we have the standard test error where we have x as input and y as output, and we compute the loss with respect to a particular loss function that we consider. For example, MSE we can consider, and we take the x minus y whole square and like we sum it over all the samples, and that is our loss function, and that is dependent on the network parameters theta, right? So that is our standard setup, and here in this paper they are proposing like changing the network itself, like the theta, by like we are using the input to change the network parameters. So that is the main idea. So, and this we are doing it during the testing, so that we have to remember. So this is the algorithm. So like in standard setting, like we have the main task and we update the network parameters, minimize this particular loss function with respect to network parameters. We have to find the parameters that gives us the minimum loss, right? So that is our main supervised setting, where we have actually the targets corresponding to the input. And now let us consider that we have a network with some number of layers, let's say k number of layers, and now like the algorithm is such that we fix a certain number of layers which will be shared across two tasks, right? So we will be having an auxiliary task where we update the parameters of the auxiliary task separately and the main task separately, right? So we will be having two different tasks, and the total parameters of the network will be halved, right? So like we will take certain number of layers which will be shared for main task and this auxiliary task, and we have separate heads for main task and the auxiliary task as well, right? So the first k layers, small k number of layers, we use it for like shared feature vector extractor, okay? So that is the shared part of the network, and for the auxiliary task we have separate set of parameters, and for the main task we have again separate set of parameters. I will show the block diagram so that you will get an idea. And now we carry out the training by minimizing two loss functions, right? So one is the main task loss and the other one is the self-supervised loss, right? So here the auxiliary task means that we are considering a self-supervised loss. Okay, so since we don't have any targets for the test signals, we'll consider a self-supervised loss, and we try to reduce the loss with respect to the self-supervised loss. So to put it in a simple block diagram, so we have this theta e, which is shared between auxiliary task and the self-supervised main task. And for main task we have true targets. Okay, so for example, if we are given an image of bird, our target is actually bird. Okay, so that we know while training for any data set. But during testing, if we are getting some other picture which is not seen during training, we actually don't know what the actual target of that particular test sample is. So how do we find the loss with respect to like such kind of examples? We design a self-supervised task, right? So what kind of self-supervised task we can design? Like there are multiple number of self-supervised tasks that we can design. One example is that we can rotate the input image and try to predict how much rotation we have applied. Okay, so this we are introducing, like we are getting the labels from the input itself. This we call it as self-supervised task. We get the labels from the input itself, right? So other than this, we can even like remove some parts of the input signal and we try to predict that particular part. Okay, so we can remove like a block of the bird image and we try to predict that block. So that is called like self-supervised task. We are actually making the targets from the input itself. So we have now two tasks, one which is dependent on the labels and the other one which is not dependent on the labels, right? So we can compute it for any test sample, right? So now we train the network using these two losses. Okay, so we combine the losses and we train the network using these two, right? So during testing, we don't have any labels, so we don't have any loss coming from the main task. So that cross mark represents we don't have any label. And from the self-supervised task, even for any like any image that we are given during the testing time, we can like always rotate it and get the labels, right? So that is self-supervised task. We can always do that. and we can get the loss from that task always, right? So during testing, what we do is we compute the loss with respect to that particular head, right? And we back propagate it through theta e, right? So theta e is shared between both the self-supervised task and the main task. So we update theta e, and this updated theta e is used to compute the final output. Okay, so that updated theta e will be used to compute the theta, the final, whatever the class that we wanted to predict, we will predict it using the updated theta e. So that is the idea, right? So they are designing a self-supervised task along with the main task, where we can use self-supervised task during testing to update the network parameters, and that's where like the parameters of the network are dependent on the input now, right? So whatever the input is, like we update the parameters depending on the input, and now we use this updated parameters to compute the final class. So this is the main idea, and I don't wanted to talk about like all the results that they have presented in the paper because those might not be relevant for us. So I wanted to show some examples where it actually worked. So for example, this elephant image, the actual network which is fixed, it predicted it as dog. Okay, so that's where you see at the 0, like when we don't update any network parameters, at the 0th step it predicted it as dog. That's why like likelihood of that particular class is higher at 0th time step, and the likelihood of elephant is lower than dog. So like for any like if the network is predicting it as dog, like we will assign the label as dog for this particular example. And now if we update the gradients, right? So if we update the network parameters using the self-supervised task, you can see that the likelihood of the elephant is increasing, which means that the network is giving like correct label when we update the network parameters based on the input, right? So this is one very good example where they have shown like how many gradient steps we have to take to change this label from like dog to elephant. So this is what they are showing, and there are some negative examples also, like first see positive examples. So like dog, after like using this kind of test time training, it predicted it correctly as elephant, and again like the other ones also. For example, the last one, which originally was predicted as car, and then after updating the parameters, it predicted as bus. But there are some negative examples also. But if you can see, like we cannot actually like predict the correct this one from the second, the middle figure, right? So you can't really see snake there. So it's reasonable that it makes mistake there. Okay, so like when compared with the positive examples, the negative examples are more difficult, I can say, right? So that's what the test time training is. Now the question is how we can use it for speech enhancement, right? So the auxiliary task, so for the network to perform better on like any task, the auxiliary task that we are designing, those gradients has to be correlated with the main task gradients, right? So for example, if we take, in this case, they are not directly correlated, so they haven't considered like, they are showing some gradient correlations, but so for any task to be successful, like the self-supervised task to help the main task, those gradients has to be correlated, right? So what kind of self-supervised task we can design for speech, right? So there are a lot of self-supervised tasks for speech to learn the representations, and there are mainly three different kinds of self-supervised representations, and we have contrastive self-supervised models where we take the model and we try to predict the immediate next samples, and we wanted to improve or increase the likelihood of predicting the next few samples, and we wanted to reduce the likelihood of predicting negative samples which are coming from a different utterance or something, right? So that kind of model is called contrastive loss, where we are trying to increase the contrast between predicting the next samples, immediate next samples, and reducing the likelihood of predicting the samples that are not coming from the same utterance. And we have predictive models where we try to predict the inputs. So for example, we can mask some of the inputs of the utterance, and we try to predict them using the network. So those kind of things are predictive models, and we have generative models where we are trying to generate the next few things, next few samples of the utterance. Right? So where they are using variational autoencoders or things like that. So these are all okay. So but we don't know like which task we have to take. Right? So as we have seen, like the gradients has to be correlated at the end. Right? So now the question is why to go for this kind of self-supervised tasks which are not directly related to the input or the task that we are addressing, right? So we are addressing actual speech enhancement where we wanted to remove the noise from the speech signal. So what we can do is, and this is my idea, so we have this noisy signal and we add some more noise to this, right? So we add some more noise and we try to predict the noisy signal, right? So from the noisier signal, so where we have added some more noise to the signal, we try to predict the noisy signals. Now this particular task where we are trying to reduce the noise, we are not trying to reduce all the noise, but we are trying to reduce the noise that we have introduced explicitly, and this is kind of like reducing the noise only, and this gradients from this kind of auxiliary task will be correlated with the main task that we are addressing, right? So I think this particular task would be more correlated with this one. So these kind of models like noisier to noisy prediction, they have been explored like for self-supervised speech enhancement models, but like in this kind of setup they haven't explored much, right? So like they haven't used it to change the network parameters during testing, right? So like we can now use this kind of task to update the network parameters based on the input signal, like if it is coming from like a different noisy environment than the one that we have trained on, we can update the network parameters and we can get the better estimate. But obviously the computational complexity will be higher because we are actually taking a gradient step, right? So we have to compute a forward pass and then compute the gradients and take a backward pass. Whereas in actual testing time, we don't actually do this. We only do one forward pass. So actually the computational complexity is higher, but now we are not actually looking at the computational complexity, we are actually looking at how we can improve the performance even at the cost of computational complexity. And yeah, this is what I wanted to talk about. And any thoughts and suggestions? Okay.
Because there are different methods that try to modify neural networks to work with voice, certain voice. Suppose that you want to tune the parameters so it will enhance a specific speaker with the same voice. Because maybe I use it all the time on my phone. So you want to modify it so it will adapt to my voice.
Personalized speech enhancement. Yeah. So we can. Does this make sense, sir? Like using.
Yes. There are also some works on combining. So instead of using the large neural network, sometimes you want to use smaller neural networks, and you have training data. But instead of using the large training data, sometimes you have training data from a certain environment, but the noise, you don't have many examples. Okay? So if you train the whole neural network, you train on all types of noise, and if you have many examples for one distribution, you will try to modify for this type of environment. Okay? But suppose another environment which is rare, but sometimes you have it. So you want to give a more weight to that environment. So you can split, instead of working with the loss function, which is the average of all the samples that you have, you can split it into classification, transport.
Okay.
Classification, and under this classification, you give more weight to the specific distribution that you have.
Okay.
So this is
that is very interesting. And also like maybe all the noises or all the noise environments may require the full network. For example, if we have an input signal which is already kind of clean, so if we don't have to use the full network, we don't want to waste all the computational resources. We just wanted to use a part of network. But how to decide?
Yeah. So when you have a large variation in the training data, usually you need to increase the size, the number of parameters in the network, to increase the network. But if you want to reduce it, so instead of, so you can split it into classifications. So there are many attempts to try to reduce the number of parameters, to reduce the size of the network. Then you want to train it such that it will perform well based on disadvantage. Because if there is a noisy environment here, maybe it remains. So the computational complexity for the classification is smaller because you classify it and then you remain in the same environment and then you work with these parameters. So all these works are related.
Yes, sir.
Nice.
Any other questions or suggestions? Kannan sir. Yeah. We just don't want it to have any irregular. Yes. Thank you.
Hello. Yeah. So I'm going to quickly explain our analysis and our motivation using GCC fact, and then we're going to go to our explorations. We're still in the early stages, so yeah.
Basically, we are talking about a well-known application of phased array, that is like the direction of arrival estimation. So we are talking about a very common method and some challenges that when we really implement it. So it is basically for the speech localization, like to know the direction of source of the speech. So basically it involves two steps. You have to know the relative time difference of the arrival between the senses, that is the microphone, and you have to estimate the direction of arrival from the array configuration, like positions of the senses. So you can have two different models. Like coming to the problem setting, So another model that is more realistic is the real reverberant model. So that involves basically the multipath transmission, propagation, as well as like you have a reverberation, and it can be modeled like this, where there is this is the source signal, and the signal at each of the sensor is basically you can model it as an as a filter, and you have the Gaussian noise added to this. So now onwards, talk about the actual.
So in generalized cross correlation methods, we basically find the cross correlation between signals coming from recorded from a 2 microphone array. So the number of microphones is 2, and what we do is we take the time difference of arrival is the value that maximizes the cross correlation, and this is computed by taking the inverse Fourier transform of this term, which is a weighted cross spectrum here between the two signals. So the weight is this phi of f, and this is multiplied with the cross spectrum, and inverse Fourier transform is taken. So there are different choices for phi of f. So when we take it as 1, so the final signal reduces to be dependent on the magnitude of the signal. So this depends on the source signal, and it might interfere in the final computation. So when the second choice can be the inverse of the magnitude. So when this is taken, we can see that the time difference of arrival is in the phase term. So when we cancel out the magnitude, so we can get a peak at the time difference in the cross correlation plot. So the advantages of this is it is computationally efficient, and it induces short delays, but it is poor in when reverberation is high, because we considered the ideal free field model. So we are applying this mostly to speech signal. So speech signal consists of different regions. It can be a voiced region. Voiced regions are generally periodic regions, which are like vowels. Unvoiced regions, these are consonants or fricatives, different parts of the speech which are non-periodic, and then silence regions. So these peaks, these parts like this, these are voiced regions, but these are small regions over here. You can see these are, these are unvoiced regions. And this region here, this represents the silence regions. So we applied GCC FAT, or classical cross correlation, and GCC FAT on both periodic or voiced frame and an unvoiced frame. With classical cross correlation, this is the voiced frame, and this is an unvoiced frame or a fricative. So we can see that the peak is here, and when we subtract this with the maximum shift, we get the time difference of arrival. Same here, but you can see that in voiced frame there are different peaks. This is expected, so because the magnitude information is taken into account. But in GCC FAT we remove that magnitude part, so that there is only one peak here. So the challenges is the GCC FAT or classical cross correlation, it's poor in highly noisy environments. It moderately noisy and noisy environments it performs well, but it fails in when room reverberation is high. So we thought, can we use the information present in the log magnitude spectrum, or these two have different characteristics, the voiced and the unvoiced frame. Our analysis is basically mostly on the voiced frame. So we can see that there are multiple peaks here in the voiced frame, and can we explore this information, additional information in the voiced frame to come up with a time difference of arrival. So I've taken two frames of voice frame which is shifted. This is simulated, but you can see that so we are considering a method called zero frequency filtering. What it does is it tries to identify glottal closure instants where voice frames, how they are produced is when the vocal folds in the glottis, they vibrate, and the periodic puffs of air are produced, and the vocal tract shapes them and gives the voice frame as output. But so zero frequency filtering identifies these points of glottal closure. So we get peaks like this at glottal closure instant, which gives the pitch or the excitation information. So if we take this from the two frames, from microphone 1 and the microphone 2, and when we compare, we get this peaks like this, and when we subtract this, we'll get the time difference of arrival. So this was the initial exploration and initial idea. So this initial testing shows that for this frame, for one frame, it still gives the peak relatively well even at minus 10 dB SNR. We are still to test it. We are still yet to test it on more varied data like many speakers, many languages, or more noisy, more reverberant cases. But this is just simulated, and yeah, we're able to estimate the time difference of arrival with this case. So this we're still in exploratory stage. So yeah, if you have any questions or any suggestions.
evening to all. I am Chitra, a scientist from National Institute of Ocean Technology, and my other team members are Shanti Priya and Tarun Teja. They are PG students from NIT. They are unable to attend today's presentation. So I will be presenting on behalf of them. So I'll be talking about the underwater communication challenges and where our mathematical foundations on signal processing and array processing will be of useful. I'll be talking about the underwater communication as well as sub-seabed multi-beam sonar, which we are working on. So underwater wireless communication challenges. Underwater channel is time-varying multipath in nature, and it has Doppler shift because the channel itself is dynamic, and the vessels or the submersibles, whichever is in the ocean, they are also in moving condition. So it has a Doppler shift, and underwater channel has limited and range-dependent bandwidth. So if we want to communicate very long distance, we have to go for low frequencies. And if we are going for low frequencies means very limited bandwidth availability. So we will be able to communicate less number of bits information only. And underwater channel is of low propagation speed. The speed is around 1,500 meters per second only. And also the channel has ambient noise. This is another constraint. So this is a typical scenario. So this has all the effects of the communication channel challenges. See, we will be communicating from the surface ship to the submersibles. So the surface side will have all the noise components present, the ambient noise and the noise made by. So communication between the ship and the submersible is the normal communication we use. So, and in the surface side only, all noises will be present, ambient noise, the noise due to wind, waves, bubbles, all those things, noise. And then the man-made noise, ship noise, all other noise are part of the surface side. When we go deeper, actually the noise component is lesser only. So here, we have multipath components. So the signal, whatever we are sending or receiving, they will actually undergo many paths, reflections from surface, seabed, all these things, and the resultant is a combination of all signals. So this is actually the multipath time-varying transfer function. So this will undergo all this transfer function. And because of this motion between the two vessels, we have the Doppler effect. So it is very difficult to reconstruct the signal. In this underwater communication, if we want to recover the data, then we have to reconstruct the signal at the receiver. So reconstruction means then the distortion should be less. So we need to choose a filter which is suitable, which will have less distortion. So that is one of the inference. And then also we can use more than one sensor in the receiver side so that we can have more SNR in the receiver side, which will improve our SNR. So this is another inference what we have. So another topic where we are working on is the subseabed beamforming sonar. So this is actually our array configuration, the projector array and the receiver array. The footpath of this projector array will be like this. This is yellow color. And the footpath of this receiver array is like this. And the intersection of these two is our region of interest. So we will be pinging. One ping will be made by the transmitter array. So this area will be enzonified. And the all receiver hydrophones will receive information from all these area, enzonified area, and based on the beamforming angle, only that area will be of interest, and then that signal alone will be improved with the SNR, and we will be able to get a good SNR in that position. So the beam will be steered all along this transmitted path. So with this configuration, this is how this beam steering is being done. We have used delay sum beamforming, and this is the del R, and the del R is d sine theta, and here we have considered this as the theta, and these are the number of sensors. So, and in a phase representation, it is 2 pi d with sine theta by lambda, and this is the summation of signal of the beam formed signal. So based on this, we just conducted one experiment in Bay of Bengal. This is the transmitter array 1 by 6, and this is the receiver array 1 by 16, and this is the tau body, and this is the receiver array. You can see this is the transmitter array. This is actually Mills cross array configuration, you can see. So with this, we got the images of a shipwreck which was in the which was already in the Bay of Bengal. This is the depth profile, and this is the beam formed information, scanned information across track, and this is the in the elevation information of the scanned information. And this is another picture. So this highlighted information is from this object which is buried around 3.5 meters below the seabed. So that we are able to identify, and then we are able to find the dimension of that object. So this we have experimentally done, and then we are actually in the process of enhancing the signal to noise ratio and improving the system. So this course is very much useful for applying all the concepts, whatever we have learnt, and then we will be make use of this performance enhancement for this. Thank you. So, any questions, sir?
Good evening all. I am Rajeshwari from National Institute of Ocean Technology, Chennai. My team members, K. Triveni, she is a research scholar in NIT Warangal, and Kiran Deepthi, she is a BTech student. So we are going to discuss about the topic direction of arrival. So the problem statement is using music algorithm. So music is nothing but it's an acronym. It's a multiple signal classification. There are many algorithms for estimation of direction of arrival. In this talk, we are going to discuss about music algorithm. Why we chose this algorithm is it is easier to implement in hardware. That's why we chose this music algorithm. So where it is applied, this DOA where we can apply is it is mainly used the challenges present in this music algorithm. We can resolve the angle of arrival very precisely, and that is one advantage. And one more issue what we face is how to keep the elements, the spacing between the two elements. So that is another challenge we face. This is actually one source and multiple linear array of sensors we are having. In our analysis, what we have done is we have taken an array, a linear array of sensor, various elements we have taken around 18 elements, then 10 elements and 4 elements. By varying the number of elements, how it will have a performance on the output, that we will show. The basically how the music algorithm performs is, first we receive the signal from the array, then we do the covariance. First we find the covariance, we do the signal decomposition, then we find the steering, we find the product of the steering vector multiplied by the noise space, and then we find the norm of that. It's a reciprocal of that. So that will give a peak whenever the direction of array, if a signal is present in that particular direction, we will get a peak signal. So first we are showing just a signal, a burst signal we have taken, length 300 samples. This figure 2, what it represents is we have assumed two sources coming from two different directions. So why it is overlapped is actually we have given a delay between two sensors. That is why in between from 100 to, actually it is blank from 0 to 100, and from 100 to 400 signal 1 is present, and from 300 to 600 another signal is present. So both we have added physically, we have added. And this is a DOA for 18 elements. We have simulated for a direction from 65 degree and 75 degree. The number of elements we used is around 18 elements. So we can see for when the number of elements reduces, what happens. So you can see a split in between the two peaks. So that means the number of elements are not sufficient, or still if it is closer, you will not be able to resolve it. And then the next case is we are having 4 elements. See, both signals from two directions are merged. We are unable to resolve. So from this, what we can understand is the number of elements. First, we want to find out what is the resolution we require. So based on that, the number of elements need to be determined. Then what is the spacing also we need to find out. How much, what is the frequency of operation, and what will be the element spacing. That both are important. That's all. Thank you very much. Yes, sir. Thank you very much, sir.
Good evening, everyone. So our topic is related to submarine radiated signal enhancement. And my name is S. Vidyarani from NIT Warangal, and my team members are Fabim Ibrahim from NPOL and Hepzibah from LBRIT. So
we have selected a topic which is based on single channel signal enhancement. Our aim is, this problem is of practical importance. We have not done any simulation, we have just formulated the problem. We have signal radiated from the submarine. It is picked by a single hydrophone which is deployed underwater. And the signal will be transmitted to some air platform or a ship-based platform. Aim is to enhance the submarine radiated signal. We can model the received signal as sum of the submarine radiated signal plus the noise. The hydrophone, which is a sensor, is designed in such a way that the self-noise of the hydrophone is much lower compared to the complex environment, that is ambient noise. So the challenges of the problem are that x of t is the signal that is radiated from the submarine, but we don't have the exact correlation matrix of the submarine radiated signal. We only know that the signal consists of discrete tonals plus a continuous spectrum. So the received signal is a sum of these two signals, but we don't know the exact frequencies or the spectral level. We don't know. We just know that it is of this nature. And related to ambient noise, we just know that ambient noise, that is the environmental noise, we just know that these signals, the spectrum folds off with the form 1 by f squared. At the time of measurement, we can measure the C state, that is at what is the level of the ambient noise. Among these curves, we can pick one curve. But we don't know exactly the correlation of the ambient noise also as a function of time. The challenges of the problem is that how do we enhance the signal using a single channel? Is it possible to enhance using a single channel or only using multiple channel? Is this signal enhancement possible? Obviously, conventional ways we can do a short time Fourier transform. A signal enhancement can happen, but this has a limitation that if the SNR of the signal is negative, we will not be able to enhance beyond the ambient noise. So we would like to, based on what we have studied here, we would like to explore whether we can apply Wiener filter and MVDR filter in this signal enhancement problem, whether it will degrade or enhance the signal compared to STFT. That's it. Thank you.
Okay, thank you. Yeah, next, last batch maybe. Last. Anyone is there? Anyone is there to present today? Anyone? Anyone? There's 5 batches done. And tomorrow? 7 batches. So you can make any comment, general comment, so that you can.
Okay. General comment. Just a minute. I think you need to give more emphasis on the assumptions of the problem and the challenges. So this is important because when you compare different method, or you consider different problems, you have different assumptions. And it's important to note or to notice what are the assumptions that are made and what are the challenges. Okay? So try to figure out these points, because when you take material that you studied with one from one material, one problem, so you take it to another problem, it's important to see what are the differences in these two problems, in the assumptions and so on. Okay? Because when we take a solution from one field to another, it looks easy, but then you see that there are important differences, and then we can focus on these challenges. Okay. So looking forward to see